The reason we study recurrence is because there are a lot of problems that are recursive in an intuitive fashion. So we're going to look at a few of them here. The first one is Tower of Hanoi. The next one is binary search, and then we're going to look at the gossip problem. And finally, we will look at merge sort as an application of recurrence relation. So we are not going to study the algorithm of merge sort in too much detail, but we are going to just look at it to see what its complexity is. So this is the problem called Tower of Hanoi. We have a bunch of disks. All the disks initially are over here. Our job is to move them to, say, over here with the rules that the smaller disk can never be below the bigger disk. So right now, if you observe, the largest disk is on the bottom, then you have the next larger one, and the smallest disk is on top. We want this property to be true at all times. So we don't want a situation where a small disk is at the bottom and a larger disk is on the top of that smaller disk. So let's see how we can do this. If I had just one disk, life is easy. I can move that to the thing that I wanted. If I have two, then so essentially I have a problem like this. Then I can move. In the first one, I can remove this from here and put it on, say, the third one. Then I can move this one over here. So that means I will get rid of it from here and I will add it over here. And then finally I will put this one back, and that will have a total of 3 steps that I would need. More generally, if I have to solve the problem with n disks, then I could take all but one of them. And somehow move them to the third peg, then move the bottom one to the second one, and then move all these n minus 1 back over here. So that means I'll have to do the work of tn minus 1 twice, and then I'll have to do one extra work for moving the bottom disk. Now we have a recurrence relation. We can solve it and we can find how many moves I would need to move the tower with n disks to the other peg. Here is another example of an operation that we perform quite frequently, that is recursive. So here is a list. We want to find some element in this list. We want to find whether that element exists or not. So what we can do is we can do linear search, which has the complexity of big O of n, or we can do binary search, where we search for the middle element and then decide whether to search left or right. So let Cn be the number of 2-item comparisons required to know whether the item is in the list or not. And if we do this via binary search, our worst case scenario is going to be, if I have just one term in the list, then I just need to look at that one element. If I have n elements, then I can search the middle, and then depending on what that comparison say, either search the left or the right. And that means my recurrence relation is going to be like this. This one is to look at the middle element, and this one C of n divided by 2 is to look in the right half of my list. Gossiping problem is as follows. There are a set of n people. Each person has a gossip to share, and the sharing is done by person to person calls, where two parties share all their gossip. So when two people talk, they share all their gossip. Question is, what is the least number of calls required so that everyone knows all the gossip? Now we can observe that if I have just one participant, then there would be no need to gossip. There would be no need to make a call, because that one person would know all the gossip because they already know it. If I have two people, they will need one call. If I have three people, I will need three calls. Think about what I would need to do to achieve this, and so on. If I have n people, then I can observe that g of n is less than or equal to this expression, one plus g of n minus 1 plus 1. So let me explain what I mean by each of them. This 1 comes because this newest member talks to somebody in the group. Then these members that are there talk amongst themselves, which is g of n minus 1. Then somebody has to go tell the nth member what the whole gossip was, and that's why I have this one extra term. So I need two terms, one for the nth member to provide its information and one to provide all the gossip to that nth member. Here is merge sort analysis. So here let mn be the cost of doing merge sort on n numbers. So what does merge sort do? Merge sort takes an array, it divides it into two, it sorts each one. So that's why I have to do m of n minus 2 for this one, another m of n minus 2 for this one, and that's why I have 2 times f of n minus 2 times m of n divided by 2. And finally, if I have this sorted array, I have to merge them, and to merge I'm going to need order n work because I can go through the array once and merge it. M of 1, which is if I have just one element, the cost is 0, because if I have one element, the array is already sorted. You can verify that if I choose f of n is equal to n log n, this is in fact a valid solution. We can use the equation on this slide to solve recurrence relation like merge sort or binary sort. So here we have f as a non-decreasing function that satisfies the following property. F of n is a times f of n divided by b plus c times n to the power d. We have some constraints. The constraints we have are a has to be greater than or equal to 1, b has to be strictly greater than 1. That way this f of n divided by b eventually will keep getting smaller and smaller and smaller. We want c to be greater than 0, d to be greater than 0. So here is a way we can find asymptotic expression for these recurrence relations. It's going to come down to the relation between A, B, A, B, and D. Specifically, we will need to check whether A is greater than, equal to, or less than b to the power d. If a is greater than b to the power d, this expression will have this value. If a is smaller than b to the power d, we will have this value. When a is equal to b to the power d, what you'll observe is that these two expressions will actually come out to be the same thing. However, in that case, we need to add another factor, which is log n. What I want you to do is use this to go back to binary sort and merge sort and see what rule applies for each of them, and then figure out what the asymptotic complexity of each of these recurrence relation is going to be. On the next couple slides, I'm going to look at why this recurrence relation is true, but I'm not too concerned about whether you follow that, or it's not something I'm going to question you about. For our class, you will need to know how to solve this recurrence relation, which is basically given by this formula. And for that, you will need to look at whether a is greater than, equal to, or less than b to the power d and apply the appropriate case. I want to add one note. The last slide is very important. It provides a generic method for solving recurrence relation, especially when the answer we are looking for is in a big O notation rather than the precise formula. It will be important in many places, not just now, going ahead to 331. It would be important to analyze recursive algorithms and so on and so forth. We have reached the end of this module, so please go ahead and do the review quiz at this time.